Hi friends, welcome to Sri Chaitanya. This is Umasankar. Yeah, now we are in Maxima and Minima, lesson number 4. So far we have completed lesson number 3 of Maxima Minima and previously we concentrated monotonicity. Monotonicity and Maxima Minima are very very important in applications of derivatives so after tangent and normals. Because we can expect very good questions, not only in this particular chapter, mixed oriented questions even for mains and advanced examinations also. That's why I'm very much interested and concentrating more on theoretical aspects of this one. Once after completion of this, we will solve some other problems also. Now, in our lesson number 3, what I told, when a function will exist, the function possesses maxima and minima, and what is the necessary and sufficient conditions in that aspect that we have discussed. So my friends, now here, what is the beauty of a second order derivative? Suppose if anybody is asking you what is the geometrical interpretation of continuity, then immediately you are in a position to tell, okay, if I, without lifting my hand, if I am drawing the free sketch of the curve, then simply I can say that the curve is continuous, otherwise the curve is discontinuous. This already we told. Even for differentiation also, what is the beauty of the first derivative? That means if there exists a tangent is possible to draw at each and every point on the curve, definitely I can say that the curve is differentiable. That is geometrical interpretation. So what is the beauty of first derivative? Just by finding the tangents and with the help of the tangent, what kind of things that we can identify with the help of the first derivatives, we are understanding the behavior of monotonicity of the curve. That means whether the curve is increasing or decreasing, if so, at what interval it is increasing, at what interval it is decreasing, and what is the necessary condition for finding maxima and minima, the first derivative and the role of the first derivative is there. Now here, this is the higher order derivative, that is second derivative here we are concentrating, and this is called second derivative test also I can say. So use of second order derivative in ascertaining the maxima or minima. See my friends, suppose this is the situation. Suppose this is my curve, and if for this curve, this is A, and this is neighborhood of A. This is A, and this is neighborhood of A, and this is B. X is equal to B, and this is neighborhood of B. This is a curve like this, situated like this, and it is a continuous curve, and moreover it is a differentiable curve. That means at each and every, there is no breaks at all, continuous, and it is a differentiable means at each and every point on the curve, as I shown in the figure, tangents are possible to draw, and this is the neighborhood of x is equal to a, which is a minus h comma a plus h. See, when can we say the curve is increasing according to derivative language in a particular neighborhood? When dy by dx greater than 0, simply I can say that the curve is increasing. Whenever dy by dx less than 0, that means derivative of the function is less than 0 in that neighborhood, simply I can say that the curve is decreasing. See, dy by dx greater than 0, the curve is increasing, and dy by dx less than 0, the curve is decreasing. That is rate of change in the function. That we are based on the rate of change in the function, we are identifying the behavior. See here what happens. In a minus h to a plus h, dy by dx, it is what? If the function dy by dx continuously decreases means what? Dy by dx continuously decreases means what? Continuously decreases means what? For x less than a, dy by dx is decreasing, and for x greater than a, it is decreasing. That means it is like this. So, as shown in the figure, it is clear that as x increases from a minus h to a plus h, as x increases from a minus h to a plus h, when x increases from a minus h to a, your curve is increasing, okay? and after that the curve is what? Decreasing. Okay, that means, and at dy by dx the derivative becomes 0. At dy by dx the derivative becomes 0. So when can I say that dy by dx continuously decreasing? When can I say that dy by dx continuously decreasing? If its second derivative is less than 0. See, when can I say the function is decreasing? F is said to be decreasing if df by dx less than 0. When can I say the curve f is or the function f is increasing? Df by dx greater than 0. Clear na? When can I say df by dx is, if my curve is df by dx, this is my curve, or dy by dx, this is my curve, if it is my curve. When can I say dy by dx is decreasing? That means derivative of this, that is d by dx of dy by dx. That is nothing but what? D square y by dx square. If d square y by dx square is less than 0, then derivative is decreasing. Whenever d square y second derivative is less than 0, then I can say that the curve is dy by dx is continuously decreasing. So whenever the dy by dx is continuously decreasing, then what will happen? At that particular point, the curve situated like this. The curve situated like this. Similarly, whenever d square y by dx is, that means the second derivative is greater than 0. That means second derivative is what? Dy by dx is first derivative. Dy by dx is first derivative. It is, when can I say this is increasing? That means its derivative is greater than 0. That means d square y by dx square is greater than 0. Whenever d square y by dx square greater than 0, it is continuously increasing. It is continuously increasing. So whenever the function is continuously decreasing, and after that, at a particular point, it is continuously increasing, then at that point, the function has what? Maximum and minimum. So what I am going to say is, at a local maximum, first of all, differentiation of the function becomes 0, and the derivative of the second derivative of the function is negative. That is, it is decreasing. Otherwise, if it is not decreasing, what will happen? It go like this, upwards. The second derivative becomes 0, then only that is why the curve is like this. If the beauty of the second derivative is 0 means what? Until that point it is increasing. After that again it is decreasing means what? It is like this. That means the second derivative is less than 0. Again I am stressing, please don't get any confusion. Suppose if y is my function, when can I say this y is increasing? When dy by dx is greater than 0. When can I say this y decreasing? This dy by dx less than 0. Suppose my dy by dx is my function. When can I say my dy by dx is increasing? The derivative of this function is greater than 0. What is the derivative of dy by dx? That is d square y by dx square is greater than 0. And when can I say this dy by dx is decreasing? The derivative of the function is less than 0. What is d by dx of dy by dx? D square y by dx square is less than 0. That is the beauty of the second derivative. So what will happen suppose dy by dx is increasing. That means the curve is going like this. Suppose the situation is like this. Listen it very carefully, very carefully. So imagine a continuous curve. When dy by dx is greater than 0, what does it mean? Yes, till at a particular point the curve is like this, increasing, and at that point derivative is 0, so it stops. Again after that, again the curve is decreasing. Decreasing means what? D square, the derivative of the function is what? Less than 0. That means d square y by dx square what? Less than 0. So when dy by dx greater than 0 and dy by dx is equal to 0, and when d square y by dx square is less than 0, then only what will happen? The curve coming down, and at that situation I can say that the function has maximum. The function has what? Maximum. Similarly, when dy by dx, suppose, say, consider next concept. Suppose this is my function. Suppose this is situation. Dy by dx less than 0 means it is coming down, decreasing. And at this point it is 0, means it's sitting down. And after that, if it is increasing, means the derivative is increasing, means what? Second derivative is greater than 0. Second derivative is greater than 0. So, whenever dy by dx less than 0 and dy by dx is equal to 0, and after that d square y by dx square greater than 0 means what? The curve goes like this. The curve goes like this. If this is a situation at this point, what will happen? The function has minimum, local minimum. So, my friends, the beauty of the second order derivative test is, so whenever d square y by dx square is less than 0 and dy by dx is equal to 0, at this point the function has a local maxima. And whenever dy by dx is equal to 0 and d square y by dx square greater than 0, then the function has what? Local minima. First, whenever dy by dx is equal to 0 and d square y by dx square less than 0, it has local maxima. Whenever dy by dx is equal to 0 and d square y by dx square greater than 0, it has minima. That is the beauty of second order derivative. And suppose if f of a has maximum value of the function, then what will happen? So, at that particular point, your derivative, first derivative is 0 and if your second derivative is less than 0, and the value of the function f of a is called what? Maximum value. And if f dash b equal to 0 and f double dash b means second derivative, f dash b means first derivative. F dash b means if y is equal to f of x, f dash b means dy by dx at x is equal to b. F double dash b means if y is equal to f of x, that is d square y by dx square at x is equal to b. Whenever dy by dx is equal to 0 at x is equal to b, that is f dash b equal to 0, and f double dash b, that is d square y by dx square at x is equal to b, greater than 0, then I can say, and then the value of the function at x is equal to b is what? Minimum value. See, suppose at some point the second derivative is 0. What will happen? If second derivative decreases, then until that point it goes like this, and if second derivative less than 0, that means decreases, the curve coming like this. And if second derivative, if first derivative is greater than less than 0 and at that some point 0 and second derivative is greater than 0, the curve is going like this. Suppose second derivative is 0 at that particular point, what will happen? This test fails. Test fails means what? Second derivative test fails. Then at that juncture what to do? We can go for another derivative, that is third derivative we can apply. Third derivative we can apply. On the same line, what will happen? If third derivative is less than 0 at that point, then we can say that at that point the function has maximum, and f of a becomes maximum value. If third derivative greater than 0, at that point the function has minimum, and at that point the functional value is minimum value. Suppose third derivative 0, then third derivative test fails. Then at that juncture we can go for fourth derivative test. Like that, so many tests will exist for a continuous curve, provided the function has that kind of higher order derivatives exists. Don't worry, in your syllabus only up to second order derivative is there, so they may give the curves processes until the second order derivative only. Clear, my friends? So here I am giving the working rule to find the maxima and minima of a function and how to find the maxima and minima value of the function with the help of the first derivative test as well as the second derivative test. Here the working rule. According to the first derivative test, this is a first derivative test, what to do? Suppose y equal to f of x is given for you. Find dy by dx and equate it to 0 and solve this for real values of x. Say the values are a, b, c, etc., etc. These are the values of x. Take the at x is equal to a. What to do? Take the neighborhood of a. This is a. Say take a minus h and a plus h. Then find the sign change of dy by dx. Find the sign change of dy by dx in the left neighborhood of a as well as in the right neighborhood of a. In the left neighborhood of a, suppose dy by dx is greater than 0 and in the right neighborhood it is less than 0. What will happen? Situation is like this. So at this particular point the function has maxima. Or whenever this dy by dx less than 0 and when in the left neighborhood of a and dy by dx is greater than 0 in the right neighborhood of a, that means the situation is like this. Then in this case we can say that the function has minima, local minima. So this is about the first order derivative test. Suppose dy by dx does not exist. Suppose dy by dx at x is equal to 0 is 0. Then we can go for what? Second derivative test. What is the second derivative test? With the help of second derivative test, what can we do? So, suppose y equal to f of x is given for you. First, what to do? Find dy by dx and find dy by dx and equate dy by dx to 0. Solve this for real x. Solve it for real x. And let the values be x is equal to a comma b comma c, etc., etc. Now find the second derivative also, d square y by dx square. Now at x is equal to a, what I am doing is find second derivative at d square y by dx square at x is equal to a. If it is less than 0, then I can say that your function f has maximum at x is equal to a and the maximum value is f of a. Suppose if d square y by dx square at x is equal to a is greater than 0, then your function has minimum at x is equal to a and minimum value is f of a. Suppose if d square y by dx square equal to 0, what will happen? Second order derivative test fails. If d square y by dx square equal to 0, but d square y, d cube y by dx cube not equal to 0, then I can say that the point is point of inflection. At that point of inflection, the derivative, if the function has neither maxima nor minima. So like this, we can apply second order derivatives, third order derivatives and fourth order derivatives. So what is the beauty of first order derivative? It finds whether the function is increases or decreases, or somehow if dy by dx does not exist, then at that particular point, if d square y by dy by dx does not exist and d square y by dx square equal to 0, then at that particular point I can say that exists, then I can say that the point is point of inflection. And the beauty of the second order derivative is, if d square y by dx square greater than 0, the curve is concave up, and whenever d square y by dx square is less than 0, the curve is concave down. So if anybody is asking you about what is the beauty of second order derivative, then immediately you tell, okay, if second order is positive, second order derivative is positive, it is concave up. Whenever second order derivative is negative, it is concave down. See, these are the steps. In first step, what is there? If when possible, draw the figure to illustrate the problem and label those parts are important in the problem. Constants and variable should be clearly distinguished. It is, if it is possible, because for simple curves it is possible to find easily can assess the maxima and minima. Suppose second step. Suppose y equal to some function in x and y is given. You express that function as a single variable function. That means you write the function in the form of y is equal to f of x only. Because we are now concentrating, or as long as we are dealing all the things only if the function is in the form y is equal to f of x. That means x is the independent variable and y is the dependent variable. Then what to do? Then third step. Find dy by dx and equate it to 0. If I am equating to 0, what will happen? I will get a point of extremes or stationary points I will get. The points where dy by dx equal to 0 becomes what? Stationary points. Okay. So that means next what to do? Find all functional values at dy by dx including end points or something like that. So what I am saying is, if find, as I said, no, in the neighborhood, you take one point and you find the sign changes of dy by dx. If dy by dx greater than 0 and in the left neighborhood and dy by dx less than 0 in the right neighborhood, simply I can say that at that particular point the function has maximum, otherwise the function has minimum. If there is no change, the point is called the point of inflection. So that's why. But if dy by dx changes a sign from negative to 0 to positive, as x advances through x0, there is minimum. If dy by dx does not change its sign, then neither maxima nor minima at that point is called point of inflection. Suppose if the function y is equal to f of x for only limited range values in closed interval a b, then examine x is equal to a and x is equal to b for possible extreme values. See my friends, as I said, now suppose if your function is continuous and it is at end points, if the function is monotonically increasing, strictly increasing or strictly decreasing in a closed interval a b, then at x is equal to a and x is equal to b, it means at extreme points itself the function has a maximum and a minimum respectively. See, these are all the techniques to find based on the behavior of the function to identify the maxima and minima values. Clear? So the significance of second order derivatives and point of inflection, that here we are concentrating, that already I told. The sign of second order derivative determines the concavity of the curve. This already I told. Such points such as C and E on the graph where the concavity of the curve change is called point of inflection. See, at C and at E, what happens? Here up to C it is like this, up to C it is like this, and after C the curve is like this. That means if curve is like this, this is called concave up. If curve is like this, it is called concave down. So until that point, if curve changes its nature, means concave down to up or up to down, then those particular points are called what? Point of inflections. Geometrically it is very easy, but practically, okay, on paper, how can we solve? So that's why whenever second derivative greater than 0, it is concave up. That means the curve is like this, concave up. What does it mean? If curve lies below the tangents, then I can say that the curve is concave up. Concave down means what? If curve lies above the tangents, then I can say that the curve is concave down, concave up. So this is the condition at which the curve for concave upwards, and d square by dx square, that is second derivative, is negative for concave downwards. And at point of inflection, what will happen? Second derivative is equal to 0, and find d square by dx square changes a sign or not. Okay, point of inflection can also occur if d square y by dx square fails to exist. This already I told. Point of inflection can also occur if second derivative fails to exist. See, on this one line, this is the best example where second derivative fails. That's why graphically this is the first fundamental point. Whenever curve changes its concave up to down, after crossing that point, the point is called point of inflection, or down to up, then I can say that the point is called point of inflection. So literally on paper and solving the problems, these are the terms and conditions for testing the point of inflections or for identifying the point of inflections. Sometimes with this example, what I am going to say is point of inflection can also occur if second derivative fails to exist. Okay, second derivative fails to exist. That means does not exist. Means left hand derivative may exist, right hand derivative may not, or both may exist, not equal, or left does not exist and right may exist, like that. Clear? Now, see some of the standard models and important points to identify the stationary points or critical points or monotonic points or extreme points. These are some standard and suitable examples. With these examples, what I am going to say is, in an open interval, see, whenever open interval is given for you, and if it is not possible to ask to find maxima or minima value, okay, suppose y equal to x I have taken in open interval 0, 1. If anybody is asking you to find maxima or minima value in open interval f of x is equal to x defined in open interval 0, 1, if anybody is asking you to find what is minimum, what is maximum, don't say that f of 0 is equal to 0, which is minimum, and f of 1 is equal to 1, it is maximum, because they are not exist. And moreover, those points 0 and 1, they are not in the domain. That's why one should have the basic knowledge on the graphs. If you are thorough with basic graphs, you can do wonders. So be careful with open intervals. Be careful with open intervals. That's why in the beginning of the session also what I told, whenever we are talking about maxima or minima or monotonicity or whatever it may be, that points are the points in the domain of the function. Clear? This is one important point. And another. And see this graph. In this -1 to 0, this is my graph. So this is in -1 to 0, this is my graph. This is line. This is x plus 1. And at 0, it is 0. And for 0 to 1, this is my graph. So what happens? Your function is defined in a closed interval -1, 1. Your function is defined in a closed interval -1, 1. It is not continuous. Though it is not continuous, but it has maxima and minima. At x is equal to 0, obviously it has maxima, minimum. Okay, note that even a single point discontinuity can help a function from having either maxima and minima value in closed interval. Based on this particular type of models, questions were repeated and they were asked in advanced examination, not in mains. That's why I am focusing more. You collect this kind of examples. You gather it. And this kind of examples are available in our material and moreover the books that I have suggested in our previous video. And coming to extremum values. See, this is the graph. What is this? This is a discontinuous curve. Of course, this is continuous, but at this point the curve is not differentiable. And of course, it is continuous. And it is at this particular point the function at C, the functional value is different. It is not continuous actually. But here what happened? Absolute maximum at x is equal to C, because among all values in the neighborhood of C, if you have find f of C, this is the absolute maximum. Absolute is maximum is nothing but the greatest maximum. When compared with f of A and f of B, of course, there is no point at all. and when compared all values in closed interval a comma b or closed a open b, at x is equal to c, the point it has what? Local absolute maximum. And at x is equal to a, it has what? Absolute minimum. And here at x is equal to c, it has a maximum, no minima. This curve has no minima. That means sometimes only maximum will exist, sometimes only minimum will exist. Try to understand the behavior. And here local maxima at x is equal to c, no minima. At x is equal to c, it has only what? Local maxima, no minima. Not necessary that both maxima and minima will exist, provided if the function is not continuous. If the function is continuous in closed interval AB, then between two consecutive maxima there exists a minima. Between two consecutive minima there exists a maxima. But here there need not be continuous curves, and always, and moreover they are not defined in closed intervals. They are not defined in closed. This is the beauty in open intervals. See try to understand the behavior of the function in open intervals. Whenever situation given like this, then draw the graphs, and based on that you decide it properly. Whether the function has local maxima or minima, at what will exist, you can identify. See, my dear friends, these are the beautiful examples. See, up to here, this is what? Concave up, and after that, this is concave down. This is concave down, after that concave up, concave down. This is concave up, concave down. And these points at x is equal to c, at x is equal to c, at x is equal to c, they are all in domain of the function only. This x is equal to c, now called point of inflection. So at this point of inflection, it has neither maxima nor minima. At this point of inflection, it has neither maxima nor minima. So these are the basic and different concepts one should learn and practice in competitive examinations. In general, they are asking this kind of principles only, problems based on these principles only. And of course, my friends, there are some geometrical problems and some geometry problems interrelated with maxima and minima. And for that geometry, to solve those problems, here I am giving the most important formulae. Of course, they are very familiar formulae, you just follow, go through them. What is volume of the cuboid is given for you. That is LBH, length into breadth into height. Surface area of the cuboid, 2 into LB into B, LB plus BH plus LH. Volume of the prism, that is area of the base into height. Lateral surface area of the prism, perimeter of the base into height. Lateral surface area, total surface area of the prism, that means lateral surface area plus lateral surface plus 2 area of the base. This is all are what? The sides, the lateral surfaces of the prisms are all rectangles only. And volume of the pyramid, that is 1/3 area of the base into height. And curved surface area of the pyramid is one half of perimeter of the base into slant height. And the slant height of the pyramids are in a triangles shape only. For to solve some of the geometry related maxima minima type of problems, this information is useful for you, just to practice it, otherwise leave it. But those who are preparing for advanced examination, this information is somewhat necessary. For mains, it may not be. But this is important, because you can expect good problems even for rate measurement also. What is volume of the cone? 1/3 pi r square h, and what is r, and what is h, and what is the surface area of the cylinder? 2 pi r h. What is total surface area of the cylinder? That is 2 pi r h plus 2 pi r square. And what is volume of the sphere? 4/3 pi r cube. What is surface area of the sphere? 4 pi r square. And what is area of the right circular sector? That is half r square theta, where theta is in radians. These are the most important areas you have to practice. Hope, my friends, if you like this, you please share and subscribe my channel, because the information, the theoretical information, which information is very, very relevant and useful for competitive examination, that only I am concentrating here. And that information is always helpful for you to solve some of the problems. If you are good at the theory, you can solve problems, because for solving the problems, the concepts are very finite. Wish you all the best. We will meet in mean value theorems next. Thank you.